Hello everyone. This is part 3 of section 2.2. Last time we looked at solving initial value problems when given the complementary and particular solutions. So now we look at a special method, which is referred to as reduction of order. And the first page is the theory and the method explained. So we look at a general second order homogeneous differential equation, but not with constant coefficients, but where the coefficients are functions of x. And we consider that we know one solution. So we suppose that one of the solutions is given to be what we call y1 of x, or just y1. And we assume it's a solution to this general second order homogeneous differential equation, again not with constant coefficients. What we want to do is find a second solution, because we know there's two solutions, and we consider that second solution to be some function which we're calling v of x times the first solution. And we're going to substitute that into the differential equation and attempt to find v of x so that y2 is linearly independent of y1 and is also a solution to this differential equation. So that's the idea. So if y1 is a solution, we say y2 is vy1 is also a solution where v is a function of x. That means we need the product rule to find the derivative of vy1. So treat it as u times v. I guess that's confusing, right? Let's do a and b. So for the first derivative, because we're going to take two derivatives and substitute it into this general equation. So by the product rule, first factor, v, derivative of the second, derivative of y1, we just call y1 prime, plus the second factor, y1, derivative of the first, derivative of v prime, and then we do the product rule again on each of those terms. There's nothing to factor out, so two separate product rules, and we'd have first v, derivative of the second, derivative of y1 prime would be y1 double prime, plus the second factor, y1 prime, times the derivative of the first, and derivative of v is v prime. Now, let me make this plus a little bit more exaggerated, and that would be here. So we realize that these two terms are the result of the product rule on this term, which would be first factor v prime, derivative of the second, y1 prime, plus the second factor y1 times the derivative of the first, and the derivative of v prime would be v double prime. So then notice that these two terms are like, which combine to give us 2v1, or 2v prime, y1 prime. Okay, so now if we substitute everything into the general equation, we'll get rid of the functional notation, and we'll just call it y double prime plus p, y prime plus qy, where p and q are functions of x. Okay, these three terms are y2 double prime, this term y2 prime, and then we have the vy1, which is our y2. Oops, subscript, sorry. Okay, so we make the substitutions, and we just recopy the first three terms, distributed the p. That's basically all that happened in this step. And then we gathered things together with regards to the v's. That is, we have the v double prime here, and I put the y's, the functions that weren't involving v out in front. I listed those first. So here's the v double prime. Let's look for some v primes. Okay, so from those two terms, factored out of v prime, we were left with 2y1 prime plus py1. So those were from that, and then the remaining terms all just involve v. And factoring a v from those, we're left with y double prime, y sub 1 double prime, py sub 1 prime, and qy sub 1. So that was from the v's. Now, since y1 is a solution, we know that the original equation was y double prime plus py prime plus y equaling 0. So if y sub 1 is a solution, then y double prime plus py sub 1, y sub 1 double prime plus py sub 1 prime plus qy sub 1 must be 0, because it's a solution, so it satisfies this equation. So it must be equal to 0. So basically this term is then going to be equal to 0. And we just have the first two terms involving v double prime and v prime. So basically we've reduced the order because there's no v anymore. And what we're going to do is we're going to let w equal v prime. So if w equals v prime, then w prime is v double prime, and our equation becomes y sub 1 w prime plus that quantity times w, because w is v prime and v double prime is w prime. And then from there we'll be able to solve by separation of variables, and that always will work. And then after we solve for w, we're going to integrate to find v, because w is v prime, because v prime is w. So then if we integrate w prime, we're going to find v. And then finally we substitute v back into our original assumption that y2 was vy1. And that's the process, theoretically. Ours will be easier because we'll be given the function y1 and we won't have to deal with p's and q's and things. And here's a summary of a little 5-step process to consider. The first two steps are really rather easy, as we'll see through our examples, because all we're doing is we're letting y2 equal vy1, and we replace y1 by what it was defined to be. And then we find two derivatives of that and substitute into the given differential equation. And then that's the time that we reduce the order by letting w equal v prime, and we solve for w by separation of variables. So then we let that w equal v prime and integrate to find v, and then finally substitute the v into our original assumptions. And I'm saying choose the constants appropriately. We'll see through our example exactly what that means. So here's an example. We've got two of them to go over. And it says use reduction of order to find y2 given y1 is a solution. Okay, so we always start by letting y equal vy1 be a second solution. substituting, we would have y equaling vx cubed, because y1 was given to be x cubed. And then we're going to find two derivatives. So y prime would be the first v, derivative of the second, derivative of x cubed, 3x squared. So we'll say 3vx squared plus the second function x cubed times the derivative of the first, and in general the derivative of v is v prime. So v prime x cubed. And then we need a second derivative. And the second derivative is, so basically this is step 1. And here's step 2, finding two derivatives. So the first factor, 3v, derivative of the second, derivative of x squared, 2x. So that would make 6vx. Plus the second factor, x squared, derivative of the first, and the derivative of 3v would be 3v prime. So 3v prime x squared. And let me make this plus a little bit more exaggerated. So we know that the next two terms are coming from the product rule on this term. And the first factor, v prime, derivative of the second, derivative of x cubed, 3x squared. So I'll write 3v prime x squared. And then by the product rule plus the second factor, x cubed, derivative of the first, and the derivative of v prime, in general v double prime, so v double prime x cubed. But then notice that this will always happen. We basically proved it on our previous page, that the middle terms will always combine if you perform the product rule in that fashion. So 6vx plus combining those, 6v prime x squared, and then plus our v double prime x cubed. And we substitute those into the differential equation. So substituting, still part of step 2. Let me recopy the original. X squared y double prime plus xy prime minus 9y is 0. And so we substitute, and we have x squared times y double prime. It's really y2, but I'm just treating it as y for simplicity. So we have 6vx plus 6v prime x squared, and then plus v double prime x cubed, plus x times y prime, and y prime was the 3vx squared plus v prime x cubed, and then we have minus 9y, and y was just vx cubed, and that has to equal 0. So now what we're going to do is, well, to make things simpler, let's just take a step and just distribute. 6vx cubed plus 6v prime x to the 4th plus v double prime x to the 5th plus 3vx cubed plus v prime x to the 4th, and then minus 9vx cubed must equal 0. But now this will happen every time, and we had actually proven it on our previous page that the v's are going to vanish, and that's why we choose v. Well, not really, but they will always vanish. That is, this negative 9vx cubed goes away with the 6 and the 3 of them. so that what happens is we no longer have an equation involving v's. Let's list the v double primes first. So we just have a v double prime x to the fifth, and let's write the x to the fifth in front of the v double prime, because the major thing to notice is it's the v double prime that we're interested in. So x to the fifth v double prime is this term, and then we have from the other two terms that remain, v prime is common. Actually, let's just add them together because they're like terms, and we get 7x to the fourth v prime equaling 0. And then at that point, I suppose if you wanted to make it simpler, we could divide out x to the fourth, and we just have x v prime double prime plus 7v prime equaling 0. Okay, so now is the third step. So those should actually flow rather neatly, because all we really did was make a quick substitution, couple derivatives, and substitute, and do some algebra. But now we're going to let w equal v prime, which means that w prime is v double prime. So we have x, so we now have x w prime plus 7w is equal to 0. And the order's been reduced. That is, it was second order, now it's first order. We could use separation of variables, and because we're going to use separation of variables, what we'll do is we'll express w prime as dw dx and separate the variables. So x dw dx would be negative 7w in differential form, x dw minus 7w dx. Let's see, we're dividing by, got to get the w's with the dw's, so we're dividing by a w to get dw over w, and we're dividing by x as well to get the x's with the x's, so we get minus 7 over x times the differential dx. And then we have to integrate, and if you want to, throw an integral sign in front of each side at that point. We'll take a step to show it literally. I'll actually factor out the negative 7 as well. So integrating, we get the natural log of w equals negative 7 natural log x plus, and then we'll just call this, because we generated a log over here, we'll call it a natural log. But instead of c's, we're going to use a's and b's. We're going to integrate twice, so we'll first use a. So we'll call that the natural log of a. And then we're going to Eulerize to solve for w. So w is equal to, first off, this negative 7 comes up as x to the negative 7th. So then we get ax to the negative 7th. And then is step 4, basically, where we go back to calling w v prime, and we integrate to find v. So therefore v is going to be, you could throw the integral sign in front of each side, but that'll be a times x to the negative 6th over negative 6, Then we add a constant of integration that we're going to call b. And so v is then equal to, let's say, negative a over 6 x to the negative 6th plus b. And then our final step is the fact that y2 is vy1, or in our case, vx cubed. Then we have the negative a over 6 x to the negative 6th plus b times x cubed, which would give us negative a over 6 x to the negative 3 plus bx cubed. And then let me just bring it up here to finish. So we now have that y2 is negative a over 6 x to the negative 3rd plus bx cubed. But notice that bx cubed is already a linearly independent solution, because that's what y1 was. Y1 up here was x cubed. So bx cubed is already a linearly independent solution. So now we choose our constants appropriately. So we're going to choose, because we want a linearly independent solution, we're going to choose to let b equaling 0. So that term disappears. And a convenient choice of a, in this case, would be negative 6. So that we get 1 as a coefficient. So therefore, y2 is x to the negative 3rd, or if you like, 1 over x cubed. And that's our solution. Okay, so it's a little bit of a process, and we'll look at one more example. And you could label the steps if you want, but really this should kind of flow neatly without having to use steps. Because all we're going to do is start with letting y2, which I'm just going to call y, well, actually I'll call it y2 to begin with, equaling vy1. So that would be, and now I'm just going to call it y, v times x in this case. And then we'll calculate a couple derivatives. So y prime, by the product rule, first times the derivative of the second. So v times 1 is just v plus the second, x times the derivative of the first. And the derivative of v is v prime, so v prime x. And then for y double prime, derivative of v is v prime, and then plus the product rule on this, first times the derivative of the second, so we have v prime times the derivative of x, which is 1. So let me make this plus a little bit more exaggerated again. So we know that the next two terms we're writing are the product rule on this term. So we just get again v prime times derivative of x is just 1, so just v prime, and then plus the second factor x times the derivative of the first, and the derivative of v prime, v double prime, and the x tags along. So then we can combine the v primes, so we get 2v prime plus v double prime x. Alright, so then we're going to substitute. Okay, the given differential equation was a little bit complicated looking. Xy double prime, minus x times x plus 2 y prime plus the quantity x plus 2y equaling 0. So we have x squared times y double prime plus 2v prime plus v double prime x minus x times x plus 2 times y prime, which is v plus v prime x, and then plus x plus 2 times y, and y was vx, and that has to equal 0. Okay, at that point, just to make things simpler, let's go through the algebra. So distributing this x squared, we have 2x squared v prime plus v prime x cubed. Alright, I'm distributing this negative to this x and then to each of these terms. I mean, you could do your algebra any way you want, but that's the way I'm going to think of it. So negative x times x is negative x squared times v is negative vx squared, and the negative x times x is negative x squared times this term would be negative v prime x cubed. And then similarly, I'm going to think of this as negative x times 2, which is negative 2x times this v, so negative 2xv, and then again negative x times 2 is negative 2x times this term would give us negative 2 v prime x squared. Okay, and then we'll just distribute this vx times x would be plus vx squared, and then the vx times 2 plus 2vx, and that has to equal 0. Alright, now what always happens, as we had proven, is at this point the v's go away. So look at the terms containing the v's. Here's a negative vx squared, and here's a positive vx squared, and then also there's this negative 2xv that goes away with this positive 2xv. So that what we're left with then is 2x squared v prime plus v prime x cubed. Well, let's see if we can combine anything else. Actually, the v prime x cubes actually go away as well here. So those are gone. And it looks like we just have, the only other thing left is this minus 2v prime I apologize, that there was a mistake on my part. Alright, so let's go back. I sincerely apologize. This was a v double prime. I'm not making a new video, I can't do that. So let me just, I sincerely apologize for that. I have to erase all of this. And I made a careless mistake, but these videos are very tedious to create, and I'm not wasting all that time to do the first part over again. Here was my mistake. This is x squared times v double prime x. So plus v double prime x cubed. Okay, and then the rest of this I think I did correctly, but let's double check it. Minus x times x minus x squared times v minus x squared v minus x times x minus x squared times v prime x minus v prime x cubed minus x times 2 minus 2x times v minus 2xv, and then minus x times 2 is minus 2x times v prime x minus 2 v prime x squared, and then plus distributing this vx squared plus 2vx must equal 0. Alright, now if I did things correctly, all the v's should vanish. Let's first recopy. The only term containing v double prime is the v double prime x cubed. So that's this term. Let's get rid of all the v's now. Make sure they vanish. Minus x squared v minus goes with this positive vx squared. So those guys disappear. And then this minus 2xv goes with this positive 2xv. So as expected, those disappear. And then let's see what else happens here. This negative 2v prime x squared actually goes with this positive 2x squared v prime. So we can get rid of those. And so we've got the v double prime x cubed, and now just minus v prime x cubed equaling 0. And if we divide out the x cubes at that point, we just have v double prime minus v prime equaling 0. So note how we have reduced the order. Well, now we're ready to reduce the order, I'm sorry, because there's no longer a v. So if we let w equal v prime, we know that w prime would be v double prime. So substituting, we'd have w prime minus w equaling 0. And then once again, we're going to be able to separate the variables. So we're going to call, because the order is now reduced to first order, and separation of variables will always work. So dw, this is when we call w prime dw over dx, and then minus w is 0. So separating the variables, dw over dx minus equals w, and dw equals w dx, dividing by w, dw over w is dx. We could then integrate dw over w, and integrate, that's 1 dx if you wish. So we get the natural log of w is x plus, call that the natural log of c, or natural log of a, excuse me. And now we'll solve for w by Eulerizing. So we get that w equals a e to the x. And then, since v prime is w, so let me say now, v prime is a e to the x. And then if we integrate to find v, well, integrating e to the x, we get e to the x, the a tags along, but then we'll add a constant that we're going to call b. And so finally, Again, you can label the steps if you wanted. But now finally we have that y2 was equal to vy1 but in our case it was vx because y1 was x, so therefore y2 would be equal to v, which is the a e to the x plus b times x. And so that gives us ax e to the x plus bx. But then this always happens like last time. I write it as a note. You don't have to write the note, but the term containing b is always already a linearly independent solution, because we had that y1 was equal to just x. So we choose our constants appropriately. So here we're going to choose b to be equal to 0. That's always done, because that term we want to go to 0. And then an appropriate choice for here for a might be 1. So then we finally get that y2 is 1x e to the x, or just x e to the x. Okay, so sorry for making that mistake earlier, but there's our solution, and that's the end of section 2.2.